Hi, hello, my name is Holden Weston, and today I'm going to be talking about Gramatron and effective grammar-aware fuzzing and the application of the Gramatron fuzzer. Now, that combination of words in that order may or may not mean anything to you, which is perfectly alright because it's my job here today to walk you through each individual step and explain the report and the fuzzer that is Gramatron in a very digestible and easy to understand way. To do that, we're going to need to start with the very basics. We're going to need to talk about what is fuzzing. In the world of computer science, fuzzing, or software fuzzing, is a methodology of finding vulnerabilities, crashes, and security flaws in different programs or applications. A fuzzer works by generating a vast amount of different inputs, all varied in some way, whether that be randomly or through a calculated mutation, and then feeding that to the application or program that they're attempting to find vulnerabilities in, and then looking for crashes, out-of-bounds exceptions, bugs of that nature, or issues with the program that could cause it to crash, and thus not only pose problems when it comes to the stability and usability of the program, but its security as well. It's important to note that this process happens entirely automatically. There's no engineer there feeding the fuzzer inputs. The fuzzer generates all the inputs itself and then can be run for hours and hours or days, if not even weeks. So fuzzing is pretty important to software developers and software security analysts, but it's not a solved science. There's a plethora of different ideas and methodologies currently being explored with how fuzzers can be improved and modified, and one of those ideas is the idea of grammar-aware fuzzers. So what is grammar? Grammar in the context of a fuzzer and in computer science is very similar to what grammar is like in real life. It's the structure that determines whether a, sentence, or in our case, an input is deemed correct or, syntactically valid, right? You can have a sentence that doesn't make any sense, and that's because it's not following the rules and structure based around grammar. On screen now is a very basic example of how a parse tree would represent the grammar of a sentence. Traditional grammar-aware fuzzers will use parse trees like this one to kind of break down the logic and the grammar structure behind a particular sentence to help generate those fuzzer inputs. You don't have to understand what a parse tree is. I'll get into more detail about it later and its benefits and downsides. Just know it gets much more complicated than this for an actual input that the fuzzers will be using, but I'll get into that more later. Now, you might have heard me say the phrase grammar-aware fuzzer, and to understand what that is, let's break down what a grammar-unaware fuzzer is. To put it simply, a grammar-unaware fuzzer is just a fuzzer that has no concept or understanding of what the grammar rules are for the input that the application needs. Let's say I'm fuzzing a PDF application, right? The application is gonna need PDF types to be able to be used as proper input, right? Let's say in this hypothetical, this application only ever accepts inputs that follow the grammar of a PDF that it's defined, right? Our grammar-unaware fuzzer is not going to have any context for that grammar. So let's say it's just sending purely random inputs. It's a black box fuzzer. These random inputs might just be straight up rejected because the PDF application needs every input to follow that grammar structure. A grammar-aware fuzzer would know this and be able to provide only inputs that follow the exact grammar provided by the application. So, of course, having a grammar-aware fuzzer could greatly increase the efficiency of the fuzzer because none of these inputs are going to be rejected by the interpreter or the application that we're fuzzing, right? However, this doesn't mean that every single implementation of a grammar-aware fuzzer is flawless. The authors of the paper, Gramatron, Effective Grammar-Aware Fuzzing, Prevost Srivastava, and Matthias Peyer, created a fuzzer called Gramatron with the goal of overcoming the limitations of existing grammar-aware fuzzers. In the paper, they identify two major problems. The first being bias sampling. The way these traditional grammar-aware fuzzers work is they use these parse trees that I mentioned before. And based on the parse tree, they can have skewed or biased sampling, thus meaning that there is not an equal chance of generating each outcome. It's skewed in certain ways. Let's take this really simple example of a grammar structure. I've built out the parse tree right here so you can see it in a more easy to understand way. As you can see, the statement can either be a call or a return, and call can either do a function or a B function. When the fuzzer is presented with two choices, it's going to assign 50% value to each of these different choices, right? So call has a 50% chance, return has a 50% chance, right? But this means that the actual reality of the statement breaking down into an A function or a B function is actually going to be less than that because there's a 50% chance that they get to call, and then there's a 50% chance multiplied on top of that for there to be an A function output or a B function output. So in reality, the general probability is that there's a 50% chance for a statement to be returned, and then only a 25% chance for them to reach the output that is the A function or the output that is the B function. This is inherently biased as we want the outputs to be more evenly represented. Ideally, the probability of reaching any specific output is the exact same as reaching any other output. It would be equally distributed. So in this example, because we have 3 different outputs, the probability of reaching any of them should be 33%. Obviously, you can see that's not true, and that's just the nature of the parse tree. It's gonna add some form of bias. Now, this is bad for the fuzzer because when we're generating inputs, we want the most diverse inputs that cover the greatest breadth of different types of inputs. But with this bias, it's going to lean in a particular way, and in this case, it's going to lean heavier on having more returns rather than focusing on the A and B function. So obviously, this is a big limitation in the way grammar-aware fuzzers are currently implemented. And the second problem that the paper outlines with the current implementation of grammar-aware fuzzers is the small-scale mutation. In the context of a fuzzer, a mutation is very important. It's the alteration that will happen to the inputs to generate a new input that can then be used to fuzz the application. So for example, we'll take an input. Let's say an example mutation could be a bit flip. We flip a bit, then we have a new input, and then we can feed that back into the fuzzer. Going back to the parse tree implementation of grammar in a grammar-aware fuzzer, the mutations that are performed are really small. For example, one small alteration in a subtree changes a specific single function call. For example, back to our other example, it would change instead of doing the function call A, it would do the function call B. Now, this sure is a valid mutation, but it's not a very diverse one. It doesn't make grand sweeping changes. Only that small function call is changed, which is a much more localized small mutation and might have problems getting deeper code coverage. Small localized changes like this can have a harder time finding crashes or potential bugs because the mutations aren't changing a whole lot. They aren't that aggressive and thus won't be creating that many diverse different inputs. At the core of these 2 problems outlined here are the general issues with the parse tree logic that comes with this specific implementation of a grammar-aware fuzzer. The goal of the Gramatron fuzzer is to provide solutions to these 2 problems by implementing grammar in a different way than the conventional parse trees as outlined in these 2 problems. Alright, so that was a lot of information to take in. I want to take a little quick pause to ask you some questions. 2 questions I have are, what is confusing about grammar-aware fuzzers? I know that's a lot of information and maybe there's something I'll be able to clarify. As well as, how could we differently implement grammar into a fuzzer as opposed to this traditional way of implementing it with the parse trees that I've outlined? Okay, before we dive straight into evaluating how Gramatron implements grammar differently, let's start with what they're being compared to. So Gramatron is going to be compared to 2 different variants of Nautilus. Nautilus, at the time that the paper was written in 2021, was a state-of-the-art grammar-aware fuzzer, which implemented grammar using parse trees. The 2 different versions of Nautilus that they will compare against is Nautilus P and Nautilus GH. This is important to establish because the results of the Gramatron will be directly compared against Nautilus, which is a fairly strong fuzzer to compare it to. Alright, let's get started talking about Gramatron. I've basically spent this entire presentation hammering home the point that the parse tree implementation is flawed and there's definitely room for improvement. So how does Gramatron implement grammar without using a parse tree? At its simplest, Gramatron, instead of using parse trees, uses automatons. Specifically in the paper, they refer to it as grammar automatons, but essentially an automaton is a machine that generates or recognizes strings by moving between different states. Okay, but what does that actually mean? At its core, it's really just a different way of organizing information by instead of having a parse tree, where each choice branches off into a different leaf, the automaton tracks the transitions between the different states instead. Let's go back to that original example with the statements return and A and B. Here, you can see the little orange labels. These indicate the code for the transitions. So if we wanted to go from statement to call, we would just save the transition 1, 2. Then let's say we wanted to go to the A function, we would save the transition 2, 1. And so all we'd have to save is 1, 2, and 2, 1. Now this is much more efficient because the way Nautilus implements grammar-based fuzzing is that it needs to hold the entire parse tree within the stack when it performs its mutation. This is extremely costly and inefficient and can have a time complexity of at worst big O of n. However, storing it with the grammar automatons is much simpler, smaller, and faster. Let's look at a specific example. Here we're going to use the grammar for the PHP interpreter, which is one of the interpreters that was fuzzed during one of the tests. Looking at the parse tree here, it's fairly complex and has a lot of different parts that need to be stored on the stack when mutation is being done. Looking at the automaton state change graph, while this looks a lot more complex, the only data that's being saved are those small yellow transition state IDs like 1_3, 1_1, and etc. These defined paths, called walks, are much smaller and more efficient than your standard parse tree implementation. When the fuzzer is fuzzing with the parse tree, it needs to know every single node, how it connects to every other single node, and whether each node has leaves and etc. Basically needs to know the entire parse tree. Well, with the automaton implementation, it just needs to know the different transition states and then store them in a simple array like this. Not only is this faster and more efficient, but it also allows for more larger scale mutations because we're using walks instead of storing the entire parse tree. Let's look at a simple analogy to explain the difference in mutation ability. In the parse tree example, a local small change is made from the cat sat on the mat to the dog sat on the mat. Notice how only one small part of the sentence is changing. This is because the parse tree is only modifying one node at a time. In this case, changing the noun in the sentence from cat to dog, like this parse tree above. For the grammar automaton, when mutating an input, the fuzzer is able to select a transition and then completely change the entire rest of the walk, creating a much more diverse mutation. The grammar automaton isn't beholden to only switching one singular bit. It can create an entirely new path that offers much greater mutation and thus deeper code coverage. Instead of small incremental changes, the automaton is able to make entirely new walks and entirely new paths in the form of mutation. Alright, so those examples are great in establishing our understanding of the two different systems, the parse tree and the automatons. But let's look at a more granular example that's directly from the paper, looking back again on that PHP interpreter that we were talking about before. Looking at the PHP interpreter parse tree, from the previously explained methodology, we understand inherently that the parse tree has flaws as the grammar rules are chosen randomly and not flipped to generate the most diverse inputs with greater mutation. In the top left corner, I've written in the blue box some of the grammar rules. As we can see, the statement has the choice of either being a call statement or a return statement. So now every time in a parse tree you see a statement block, it's one of those opportunities like we were talking about before with the A and the B choice. This is a random choice, which, as we talked about before, inherently will add bias because there's only a 50-50 chance that it will select call statement, which has much deeper chains that it can go into, like a call statement can become a function, which can become that random function we see at the bottom. But a return statement can only be a return. So that means even though that there are way more different, deeper possibilities that could be generated from call statement, it still has an equal possibility as return statement. Adding on to that, there's even more granular choices. The function call can literally be any valid function. You see at the bottom block, the reason there are question marks on the percentage is because there are literally so many possible functions that could be here. On the Gramatron GitHub, the JSON file that stores the different functions that could be there goes like all the way down to over 8,000 different functions. So it's probably like a 1 out of 8,000% chance you get any of the possible functions. This just further highlights the bias because before you can even roll the 1 in 8,000 chance, you have to hit the 50% chance that the statement turns into a call statement instead of a return statement. Anyways, it's pretty clear that Nautilus's implementation of the parse tree clearly has some issues when it comes to bias and mutation coverage. Now let's look at the PHP example for the automaton. I would be remiss if I didn't mention the process in which the automaton is generated. The paper goes into pretty great detail on how the automaton is set up, as it's not as simple as just converting a parse tree into an automaton with the transition states. I'm going to greatly simplify it because you only need to know like this rough part of it. So the basic idea is first it takes the context-free grammar. This is that huge file with 8,000 lines that I brought up earlier. This is the grammar for the PHP, and it's stored in a file called source.json in the PHP folder. This stores the context-free grammar, the CFG, which is essentially just the basic rules for the grammar. Then this is converted to what the paper calls grammar form. This is a form that's just easier to process and create enums, which is the next step, which creates all the different possible parser states. And then after that, finally, the automaton creates the transitions, which is what we've been talking about when we're talking about the automaton. Those are the most important parts. So after all that process is done, generating inputs for the fuzzer is as easy as taking a walk from a start state and then building that path to the final state. Let's go back to the cat example. So as we see here, the cat in yellow, this is the starting state. All that's needed to generate a new input is to have that starting state, and then the blue, which is the walk to the final state, can literally be anything else. And this mutation is obviously much more diverse and much more aggressive than the parse tree. But we can even get more granular than that. There are 3 different types of mutation operators that can happen with the grammar automaton. One is a splice, which will just simply combine two different walks. A random mutation, which will choose a point and then regenerate the entire rest of the walk. And then a random recursion would repeat recursive subwalks. For example, if an expression can be equal to an expression plus another expression, this would be a recursive subwalk. Now, the recursive subwalk, as you can see, is a pretty powerful mutation, but it comes with some problems. In the context where, let's say, once again, an expression can be equal to an expression plus another expression, this can keep recursively multiplying more and more and more until an expression is expression plus expression plus expression plus expression. This is a problem as we don't want our inputs just purely being all recursive mutations. So within the paper, they define that they've set a hard limit on the number of sequential recursive mutations. Overall, I think it's pretty obvious that the mutations from the automaton are much more effective, whether it be the slicing, random mutation, or the recursion, are just overall much more effective than the random parse tree mutations. All right, so that was a lot of information to take in. I'm going to take a brief pause to ask you guys some questions before we jump into the results and the data portion of the report. All right, first one. Based on what we talked about, how do you think the Gramatron will stack up against the Nautilus fuzzers, and why do you think this? It'll be good to kind of get your predictions in before we see the actual results from the paper, so you can kind of evaluate your understanding of the information that I presented so far. And the second question I have is, do you think that grammar automatons are the best way to do grammar-aware fuzzing? And if so, what are some potential alternatives? You don't have to have a super concrete answer for this one. I just want you thinking about some potential alternatives to automatons. There's no right answer, and I don't even have a great answer for this question either. It's just a way to get you looking at fuzzers and grammar-aware fuzzing in a different way. Okay, so at this point, I've spent 16 minutes just telling you Gramatron's going to be better than Nautilus. Gramatron is better implementation of grammar-aware fuzzing, yada, yada, yada. Let's actually look at the numbers and the results from the paper and see how Gramatron, as a fuzzer, stacks up with Nautilus GH and Nautilus P. To do this, we're not only going to look at the data, but answer the 4 major research questions. 1, does Gramatron remove sampling bias? 2, are mutations more aggressive and efficient? 3, can it find bugs faster? And 4, can it discover real-world vulnerabilities? All right, starting with the first research question, does Gramatron remove sampling bias? This question is answered using branch coverage. Here's the table that shows the different branch coverage percentages of each of the models. Of course, the N represent Nautilus and the G represents Gramatron. The results show that overall, the inputs generated by Gramatron achieve up to 24.2% more branch coverage, which means the fuzzer explores a larger portion of the grammar's behavior. So, because the mutation coverage is better from Gramatron, this means that there's some sampling bias that is being removed when comparing Nautilus to Gramatron. So, to answer the first research question, does Gramatron remove sampling bias? The answer would be yes. It does indeed remove some sampling bias. Okay, now moving on to research question 2, are mutations more aggressive and efficient? In the paper, they state that our redesigned mutation operators are 6.4 times more aggressive, meaning that they're changing larger parts of the input, and this can also be seen in the graph below. You can see that the mutation lengths for Gramatron in blue are much, much greater than that of Nautilus, thus meaning, more aggressive and deep mutations that end up being much longer. Okay, so the mutations are more aggressive, but what about efficiency? From these graphs, we can see a great improvement in the efficiency of the mutation. The speed at which inputs are generated are up to 98% faster as a direct result of the implementation of the automatons rather than the slow parse trees. As seen in the table here, the input generations for mRuby, PHP, and JS are all significant improvements. These percentage improvements listed here are what average to that 98% faster input generation speed I mentioned earlier. Here are the graphs that shows time taken to perform the different mutation types, splice, random, and recursive random. It's pretty evident from these graphs just how much faster Gramatron is compared to Nautilus. Like looking at the splice mutation and the random mutation, you can barely even see the marks that the Gramatron makes in comparison because they're just such a fraction of the speed compared to the times it takes for Nautilus to do those same mutations. Random recursive is a little bit closer, but still even then, Gramatron is still more efficient and faster than Nautilus. Okay, so moving on to research question 3, can it find bugs faster? Both Gramatron and Nautilus were run on these 3 interpreters that I mentioned before, and there were overall 10 different bugs that the fuzzers needed to find. These are listed on the left here with bug ID and bug type. You can see that there's 4 for the PHP interpreter, 2 for the mRuby, and 4 for the Jerry script. Both the 2 versions of Nautilus and the Gramatron were run 10 times for each individual bug, and then their median times and effective sizes both measured. Gramatron went 10 for 10 on all 10 bugs, meaning that every single campaign run, Gramatron was able to find the bug. Both versions of Nautilus were not able to do this. This is seen in the bolded section in the successful campaigns. This clearly shows that Gramatron's ability to find bugs is superior to Nautilus P and Nautilus GH, as at no point was Gramatron ever unsuccessful in finding bugs, where Nautilus P suffered quite a bit, especially in the Jerry script sections, and then Nautilus GH was also unable to find the bug in 3 different campaigns. However, these successes don't take into account the median time. A lower median time for a fuzzer would mean that it is more efficient, faster, and just better overall at finding bugs. The majority of the time, Gramatron was much more faster than Nautilus P and Nautilus GH. However, there are a fair few instances in which Gramatron was not faster. This is because while the mutation for Gramatron is much more aggressive and changes larger portions of the input at once, for bugs that occurred in a very specific part of the grammar, the small localized changes that came from Nautilus were actually beneficial in this area. So while yes, Gramatron is generally faster, there are still some benefits to those small localized changes, meaning there are some benefits to the way the parse tree implementation handles mutation. Alright, and finally, the last question, can it discover real-world vulnerabilities? To test this, the researchers ran a 10-day fuzzing campaign with the targets of mruby, PHP, and JavaScript once again. They found 10 new vulnerabilities as seen in the table below. These are new undiscovered bugs that no one had found before, thus showing the ability of the fuzzer to work in a real-world context on real software. These bugs were reported to the developers and maintainers of each of these interpreters and subsequently patched and fixed, which just further highlights that Gramatron is being used on real software and actually able to help developers in real-world contexts. I feel it's safe to say that Gramatron answers the research questions in a way that is satisfactory while demonstrating the benefits of the grammar automatons in many practical tests and even real-world applications. I think one possible extension for the future is highlighting the benefits of the parse tree that we saw in the median timetable in research question 3. We saw that generally Gramatron was faster, but in those instances in which the bug was localized to like a super specific part of the grammar, that actually the parse tree implementation in Nautilus was faster. And I think that could be an interesting place to explore. The logistics of how that could be implemented into the current Gramatron system aren't going to be easy questions to answer, but I think it would be an interesting place to explore to see if maybe identifying interesting parts of the code and then making those smaller, more localized mutations in areas where a bug might be present could be an interesting exploration and expansion on the project. Thank you for taking the time to listen to what I had to say. I hope you learned something and I hope it was mildly entertaining along the way. Thank you for your time and have an amazing day.